Hi, everyone. My name is Piotr Kulik, and today I'll be presenting on novel thin film materials for spintronic devices and quantum sensors. I'll, I'll dig into some of the applications of these unique materials, as well as to some of the research motivation and future directions. So I'm a new faculty at the University of Central Florida, and I just began in August. So I'm in the process of building up my lab and capability. So a little bit about the lab and what direction it's planning to take. So we would like to leverage these exotic thin film magnetic acoustic materials and multiple physical phenomena to achieve unique performances for applications from communications to sensing. And as a result, we need a lab skilled with both from RF simulation to material scientist. Currently the lab consists of two graduate students. One is a GEM scholar stemming from MIT Lincoln Labs, and another comes from a local company called AESG. With that support, we have three undergrad students helping the grad students in the lab set up and do measurements. A little bit about myself. I come from Stevens Institute of Technology, a small engineering school in New Jersey, and I graduated with a Ph.D. at Northeastern University up from Boston. So during my experience, after my PhD, I worked at a company called Metamagnetics, which was a spin out of Northeastern University, and I led their DARPA R&D efforts for DARPA Warp and DARPA COPY programs, which were geared towards RF communication devices utilizing magnetic materials. As well as I participated as a performer in the DARPA and Cubic, as well as the DARPA and Zero and DARPA SPARC programs as a performer at Northeastern University. I've been also involved in the IEEE MTT community, specifically MTT 13, which focuses on these magnetic components for these different applications and creates technological roadmaps for companies as well as academia. And I've also been involved with the Association of Old Crows, which is an electronic warfare society. That's a nonprofit society that's focused on developing solutions for electronic warfare. So my research motivation, one of the reasons why magnetic components are interesting and capable, right, is, as you can see here, we have the US frequency allocation spectrum. It's getting more and more crowded as more devices come online. It's an interesting problem. I consider the RF spectrum being like oil, right? It's limited in its use. You can't make more of it. We can just cut more, allocate more frequencies. Companies tend to bid on these frequencies and whatnot. So the goal of the lab is to combat that and develop unique solutions and technologies that allow us to share frequencies, prevent interference, as well as develop new techniques that don't rely on the spectrum. And that's where magnetic sensing and magnetic navigation come into play. In the middle, I'm showing you the magnetic fields required for ranging from an MRI scanner, 1 to 7 Tesla, to being able to sense a magnetic field from a vehicle passing, and going as far down as neuromagnetic field imaging, which requires femtotesla sensitivity to be able to basically image a magnetic field around the brain. A lot of magnetic field developments have been involved in submarines, as seen here, as well as NOAA, for example. This is a magnetic field map of the different the field distribution on the eastern seaboard. So this map is relatively interesting because it allows us to go into applications such as magnetic navigation. So your spectrum is saturated, right? Let's say your GPS is not working. What other techniques can you use to navigate? Magnetic navigation is one way. So when your satellites are down, and we've seen this type of case in recent media, we can use magnetic sensing as one technique for future navigation. So how do we do that? So currently, the state of the art in magnetic components comes from basically looking at a full duplex communication, right? So again, tackling that RF comms problem of non-interference, right? Can we communicate and provide enough isolation between our front ends to be able to share a frequency? And that's where devices such as circulators, as shown here, both in the RF and optical domain, come about. There's also developments in magnetostatic wave resonators, which I would say share a similarity to acoustic wave resonators, but are slightly longer in wavelength and are not your typical electromagnetic resonators. They have some advantages in the higher frequency ranges. Magnetometers, right? So one material, for example, the lab is looking at is called yttrium iron garnet. It's a low line width material. It's a synthetic material, but it has a high Q, and it's used in these RF circulator and filter applications, but it can also be used in magnetometer applications, which we're exploring. So right now, magnetometers, for example, here Lockheed Martin Dark Ice is a program that is looking at using the synthetic diamond magnetometers that to have magnetic navigation capabilities. However, those are large, require cooling systems, and are not really integratable. So one of the aspects of the lab is to look at these materials such as YIG and look at these different competing components and how do we reduce their size, how do we reduce their size, weight, and improve their performance. So one way of doing that is looking at the material side of things. A lot of these materials come in a bulk form fashion. They're sintered compact ceramics. There have been techniques involved in depositing these materials called pulse laser deposition, where you take this ceramic compact material, you put it in a chamber, and you blast the laser on it. It sputters, creates a cloud, and then that material gets deposited on a substrate. I've done this during my PhD work, where we've sputtered a hexaferrite material, which is a magnetic material for circulator development. However, there's a lot more applications of this tool and this deposition technique for some of these films, such as YIG that I mentioned is used for magnetic sensing and RF communication. So that is one approach that we're looking at, is taking that material, depositing thin films, and then characterizing both the RF and optical performance of the film. Parallel to that, one aspect of utilizing YIG is in parallel to the material characterization fabrication, we actually both simulate in the lab and move on towards a clean room. So lithography for fabricating this material. Of course, these materials are exotic, right? They're ceramics. They're not your typical nitrides or semiconductor materials. So there is also, development of the fabrication capability to make resonators, for example, and filters. So all in all, right, just starting the lab, what's the near-term research plan? Well, in the next year or two, we're focused mostly on building magnetostatic wave resonators, helping develop that capability here at UCF, being that building block for all these sensing and RF and optical components. Some of the collaborations I'm looking for here within the UCF community is how can we package these devices,
can we also look at other new materials, right, that provide the same phenomena? As well as outside of UCF, we've been looking at proposals with AFRL, NIST, and Northrop Grumman on how to apply this and transition some of this technology. Furthermore, while we're building wave resonator blocks, we're also looking at these sensing capabilities. So for example, here you can see a MEG image, which is used in magnetocephalography, which is used for image the brain. It requires that femtotesla sensitivity. However, the technologies that allow that, as seen by this graph in your left-hand corner, are quite large in the sensor linear dimensions. So the end require things like cooling. So SQUID, nitrogen vacancy-based sensors, they're just large. So we utilize this unique materials to make them smaller. And there's within the UCF community, as we build these sensors, we're looking at folks who could collaborate on the signal processing end, as well as the biomedical testing end, and outside of UCF, working with partners such as MIT Lincoln Labs and Johns Hopkins Applied Physics Labs to push the direction forward. Long-term research plans, taking some of the technology developed in the lithography and the pulse-laser deposition techniques to look at integrated magnetic power applications. A lot of these materials have a high permeability, which is relatively beneficial for inductor applications, and then integrating some of those applications onto ultra wide bandgap semiconductors. And that's actually been a thesis of DARPA nowadays is, how can we tackle heat thermal problems and high power applications, and this technology would be a good source of it, as well as taking the pulse laser deposition and developing other components such as high dielectrics. Pulse laser deposition is again a pretty unique tool, since it allows you to deposit materials with really complex stoichiometries, right? So can we leverage that and develop, for example, high-K dielectrics? So that ends my talk. I would like to acknowledge the College of Engineering and Dean Michael for organizing these seminars. And thank you everyone for joining today's talk. And if you have any questions,